Hello and welcome to this lecture on fundamental of electric drives. Today we will be discussing about the steady state stability of the drive system. Now, we know that a motor drives a load and in the steady state the speed does not vary. So, the acceleration is 0, it means d omega m by dt is equal to 0. So, we have a motor which is driving a load here, and this is the mechanical shaft which is coupling the motor with the load, and the motor speed is omega m, that is same as the load speed, and the motor torque is T. The load torque opposes the motor torque, that is T L, and the total moment of inertia of the system is J. Now, we have already seen in the last lecture that when we have a motor and load combination, we can write a dynamical equation, and the dynamical equation is as follows. So, this is J d omega m by dt, which is the angular acceleration into the moment of inertia, which is called the inertial torque, plus viscous friction torque or the frictional torque T f, and the useful load torque, this is equal to the motor torque, that is T here. Now, in this case we assume for simplicity that friction is 0, we do not have any friction, or we can include the friction with the load torque. So, this is combinedly known as the load torque T small l. So, in the steady state we have d omega m by dt is equal to 0, the speed is constant. So, d omega m by dt is equal to 0 in the steady state. So, if we apply this in this equation, so this quantity vanishes in the steady state. So, what we have here is T L is equal to T, or the load torque is equal to the motor torque. So, that is the steady state condition. Now, it means if we want to find out the operating point is decided by the intersection of the motor characteristic with the load characteristics. So, we have, let us say, the speed torque plane omega m and t here, and let us say this is our motor characteristic, which is T, this is, and we have the load characteristic which is this one T L, and the intersection of these two decides the operating point. It means the motor will be running at the speed and the corresponding torque will be this torque. So, this is the operating point. So, this is the motor characteristic, and this curve represents the load characteristic. Now, the question is that is this operating point is a stable operating point, that we have to find out whether this point is a stable point or unstable point. This we have to find out. Let us see how we can decide whether this point is a stable operating point or an unstable operating point. Now, in this case, let us take two examples. One example, we have the speed in the y axis, torque in the x axis. Here we have omega m and t. Let us say this is our motor characteristic T and this is the load characteristic T L. Here we have the motor characteristic T and we have the load characteristic which is T L. Now, in the first case we have the intersection which is point A, and in the second case the intersection is point B. So, we have two different examples. In one example the operating point is decided by A, and the other example the operating point is decided by the intersection, that is B. Now, we have to decide the out of these two equilibrium point, which equilibrium point is a stable equilibrium point and which one is an unstable equilibrium point, because at each equilibrium point we have T equal to T L. Now, here also we have T is equal to T L at A, here also we have T equal to T L at B. Now, what you have to do is that at that equilibrium point we will give a little bit of disturbance, we will disturb the speed, let us say. Now, if you disturb the speed, the torque will change. Now, let us say we disturb the speed, we increase the speed little bit here, now we increase the speed here. Now, when we increase the speed from this point by some value, let us say delta omega m, now we have the load torque here and the motor torque is here. Now, at this instant when we have disturbed from this was the operating point, here we have let us say omega m 1. So, we have already disturbed it, and right now we have omega m 1 plus delta omega m. Now, the motor torque in this case becomes less than the load torque. Motor torque is less than the load torque. It means load torque is more, motor torque is less. So, there is a tendency the speed to decrease, because the load will bring the speed down. The load is more, the motor which is driving the load is less. So, the load will try to bring the speed down. So, the speed will come down and this will again reach this equilibrium point here. Now, let us say if we disturb the speed in the other direction by the same amount, let us say delta omega m, we have a new equilibrium point here omega m 1 minus delta omega m. At this point, which is omega m 1 minus delta omega m, the motor torque is here, the load torque is here. So, we find the motor torque is more than the load torque. The motor torque is more than the load torque, which means the motor will try to drive the load, the speed will increase. So, the speed will increase. So, this will result in increase of the speed. So, the characteristic will be travelled in this particular fashion and then will reach this equilibrium point. So, we can say here A is a stable equilibrium point. A is a stable equilibrium point. what about B here? If you see this characteristic in this case, which is the intersection of the motor characteristic and the load characteristic, we again give a disturbance. This was originally operating at, let us say, the point here is omega m 2 and the corresponding torque here is T 2. This was the torque in this case, that was T 1 here, that was the operating point A. Now, in operating point B, the speed is omega m 2 and the torque is T 2. Now, we increase the speed by delta omega here. So, when we increase the speed by delta omega, this is our delta omega here, the new speed becomes omega m 2 minus delta omega m. So, we see that when the speed has, say, this is plus delta omega m, and we see that in this case the motor torque is higher than the load torque. So, here we have T greater than T L. So, when the motor torque is higher than the load torque, motor is more powerful than the load, speed will go on increasing. So, it means there will be divergence. It means the speed will be further increasing and the characteristic will diverge and will run away from the point B. So, it looks like that the equilibrium point B is an unstable equilibrium point. And if we decrease the speed here by delta omega m, we have got the new speed omega m 2 minus delta omega m, and here what we obtain here is that the motor torque here is less than the load torque. So, motor torque is less than the load torque. So, the motor is less powerful than the load. So, the speed will further decrease. So, this operating point will go away from B. So, this is how the operating point will travel. So, it means point B is an unstable equilibrium point. So, we have got two situations. In one situation we got a stable equilibrium point, in the other situation we have got an unstable equilibrium point. So, it means all motor and load combinations may not be stable. Some motor load combination will be stable, some will be unstable. So, we have just explained or understood this graphically. So, is there a mathematical way of arriving at the decision whether equilibrium point is stable or unstable? Now, let us try to see that. So, in general the rule is this, that if d T L by d omega m is greater than d T by d omega m at the equilibrium point, then we call the stable equilibrium point. So, this is basically the condition for stability. So, we have to check for this condition. If the condition is satisfied, we say that that point is stable point. If the condition is not satisfied, we say that that equilibrium point is unstable equilibrium point. Now, let us prove this mathematically. Now, let us see that we have the motor torque, which is given by the load torque plus J d omega m by dt here, and let us make a little bit of perturbation. It means we have disturbed this equation. So, this is a perturbed equation. When we have a change, a small change, this equation looks like this. Now, if I call this equation as equation number 1, this equation as equation number 2. So, what we will do, we will subtract equation 1 from equation 2. So, if you subtract equation 1 from equation 2, what we get is a small signal equation, delta t is equal to delta L plus j d by dt of delta omega m. Now, this is a small signal equation which is about the perturbation delta t and delta omega and delta T L, this equation is a small signal equation. Now, from this equation we can show whether a equilibrium point is stable or unstable. Now, let us try to see what is delta t. Delta t is dt by d omega, the slope of that at that point into delta omega m. Similarly, we can say that delta T L is equal to d T L by d omega m into delta omega m. So, these are the small disturbance in torque, the motor torque and the load torque, which we obtain from the slope of the respective characteristic at the equilibrium point. Okay. Now, if we substitute for delta T and delta T L in this equation, this is equation number 3. So, what we get here is the following: dt by d omega m into delta omega m is equal to dTL by d omega m into delta omega m plus j d by dt of delta omega m. Now, we further simplify this equation. If we further simplify this equation, what we get here, j d by dt of delta omega m, that is equal to dt by d omega m minus dTL by d omega m into delta omega m, or we can take everything to one side and simplify j d by dt delta omega m plus dTL by d omega m minus dt by d omega m into delta omega m, that is equal to 0. Now, this is a very important equation. This equation is a first order equation in d by dt of delta omega m. So, we have to find out the solution of this equation. So, the solution of this equation will be of this sort, that delta omega m is equal to delta omega m naught, the initial value, into 1 minus exponential minus this equation's solution is the following, that this is exponential of minus dTL by d omega m minus dt by d omega m 1 by j into t. Now, this is the solution of this equation. This is a first order equation. So, if we solve this equation, we get the solution of this particular form. Now, this is the initial disturbance. Now, if we want that finally, when we have disturbed the speed by delta omega m naught, finally the speed disturbance will be 0. If we disturb the speed and leave it like that, this would again come back to the original equilibrium point, which means delta omega should be equal to 0. So, it means at t tending to infinity, delta omega should be equal to 0. So, as t tending to infinity, if delta omega should be equal to 0, the coefficient here has to be positive. So, if for t tending to infinity, delta omega should tend to 0, we should say that dL by d omega m minus dt by d omega m should be greater than 0. It means this value which determines the decay of the exponential, this value should be positive. So, only when this value is positive, we can say that at t tending to infinity, the exponential term will go down to 0. It means, if we disturb the speed and leave it at omega m naught, as t tending to infinity, this will decay down to 0. So, for the exponential part to decay down to 0, this part has to be positive, and j is the moment of inertia which is always positive. So, the only thing is that dTL by d omega m minus dt by d omega m, this quantity should be positive. So, which implies that dt L by d omega m should be greater than dt by d omega m. So, we have proved that for stability dt L by d omega m should be greater than dt by d omega m. So, we can write once again for steady state stability, we can say that dt L by d omega m should be greater than dt by d omega m. So, we check at the equilibrium point, if this condition is satisfied, we say that operating point is a stable operating point, and if this condition is not satisfied, we can be sure that that operating point is an unstable operating point. It means, whenever we have some disturbance, the speed will diverge or the speed will not settle down to that particular point. So, we should avoid unstable equilibrium point. We should only try to see that the load torque and the motor torque combination has to be stable. Now, let us go further and we will discuss about what is called load equalization. Now, what do we mean by load equalization? Now, we have various types of load, which can be, as we already seen that we can have a fan type of load, we can have a traction load, we can have a constant power load. Now, we have some special loads which are pulsating in nature. The load torque does not remain constant, it changes with time and it goes up and down. For example, if you have seen the sugarcane juice making machine, when the sugarcane enters that machine, there is a load torque applied. When the sugarcane comes out of the machine, the load torque is 0, and this happens repeatedly. Same thing as steel rolling machine. In the steel rolling mill, the ingot goes into and then comes forward, goes into. So, we have pulsating load torque. So, an example of a pulsating load torque is the following. We have the load torque which is varying like this. It is not constant. So, we are plotting this load torque against time, this is t here in the y axis, and this is the load torque high value, this is the load torque low value TLL, and the time for which this high value is applied is called TH, the time for which the low value is applied is called TL. Now, what we have to do right now is that if we have a pulsating load torque, we have to decide a motor for this. Now, the motor has to supply the load torque. Now, should we be deciding on the high value of the load torque or on the low value of the load torque? So, we should be trying to see that the motor torque should be in between the high value and the low value. The motor torque has to change something like this. It should neither be very high nor be very low. This is the motor torque here T, and this variation is for TL, the load torque. So, the motor torque varies between minimum value, this is called T minimum, and we have a maximum value, that is the T maximum. So, in the steady state the motor torque changes between a minimum value and a maximum value. Now, how do we achieve this? We achieve this by connecting a flywheel to the motor and the load combination. So, we have a motor here which is connected to a load, so what we do here, we attach a flywheel, this is a flywheel. Now, what does a flywheel do? The flywheel equalizes the load. It means, although the torque variation is up and down, the variation of the motor torque is not as severe as the load torque. So, the differential amount is supplied by flywheel. So, this flywheel, what it does? Flywheel increases the effective inertia of the system, the effective inertia of the system. So, when the inertia is more, the combination, the motor and the load combination can supply more load torque. So, in this case the total inertia is J, which is the combined inertia, and this consists of the inertia of the motor plus the inertia of the flywheel. So, now when we connect a flywheel, we have to find out what should be the inertia of the flywheel. So, we have to decide about the inertia of the flywheel. So, it means what should be the inertia of the flywheel, so that we achieve the desired T minimum and T maximum. Now, we can do that by plotting here the motor characteristic. Now, let us say this is the motor characteristic, which is speed versus torque, speed in the y axis and torque in the x axis. This is omega m naught. So, this is a drooping profile. So, the motor behavior is known. So, when the motor behavior is known, we have to use this motor behavior to decide the inertia of the flywheel. So, we conclude for this particular class. We will continue from this in the next lecture.